of 2011. My name is Sebastian. I'm here to show you how to do double integrals through this calculation book, thanks to Richard Fogel. So what I'm going to show you through 2 and 3 is what is called double integral by rectangular regions. It means that all integrals have a base of a rectangular region of x and y, and for number 2 here, what we have is first we have the y limits, and then we have the x limits, and we have the equation within the two integrals. Now the first thing that you should notice is that these two are separated and should be kept separate. And first thing you do is just be concerned only about the y's, because we are in respect of y. So first you do the y, and you treat x as a constant, because we're not dealing with the x right now. So you do, as always, do the regular integration. So you get from 1 to 3 is 2xy minus 2y squared to the, from -1 to 1 dx, and then you expand that out as you always do, and you make a mistake because we are humans and we make mistakes sometimes. So you simplify it, and then you get this equation out right here. And now you only take care of the x's, and then you make another mistake because you're humans. That's what we do. So you do that, you end up with 16. And for number 3, same thing, only you have to have the x with the y, and then this time the x is switched, which is fine as long as you keep your variables straight. So you got x squared y dx from 0 to 1. You have the whole integral from 2 to 4 dy. Then next, what you do is just always keep the y as a constant, and then you do the same thing as integrals 3 cubed, and then all over 3, because that's the way to get it back. If you take the derivative, that's how you get back to x squared, and then you expand it, you get this, and then keep the y alone because it's only for the x's. We're only concerned about the x's right now. And then you expand that, and then you simplify it to this number right here. And then now you take care of the y's because we are in respect of y. And then you make a mistake because that's what I do. And then you take the antiderivative, then you plug in the 2 and the 4 in the correct place, you subtract it out, and we get 2. Now let's see if we got that one correct. And the reason why I wasn't able to get the other one checked is because that they only have the odd numbers. So we have number 3, and it's 2, and we got 2. So yes. But that's not enough. We have to do even more deeper research on our tree. project, and as you can see, is well done. And I have here the actual model car, that is the Silver Veil itself. And as you can see, I could do the body part right here very easily. As you can see, it can be with the regular one integral. But if you can see the fins, that go on the side are not rectangular base. They're more of a
Cartesian.
Because the on the base is a graph of parabola, that is, and the whole shape is like a half circle, but the way it increases is very big. So actually, when I was doing this project, I wasn't able to get exactly what I wanted, but I was able to get close. And with my friend David Gaskins, we were able to do the best we can, and we got a good grade on it. But I found out now that there is a way to get the fins on the Silver Veil, and that is through integral by non-rectangular bases. Okay, so this is double integrals by non-rectangular regions. That is that on the first integrand we have in the very inside we have x squared from x squared to x, which means that on the plane of x and y, it is graphing x squared and x. And the thing is basically almost like the G prime trick, if you remember. And the thing is that you just do the same thing, and here you go. You integrate it like as always, and be sure to be mindful of those things that you're doing in respect to, and then keep going. You plug in all the values that has to go with. So you plug in the x and the x squared, and then you simplify. Then you got this, and then you do it in respect to x from 0 to 1. You got this, plug in the values. You have 1 to the 5th all over 15 minus 1 to the 8th all over 24, and then it's subtracting the zeros, and we do this just in case we are wrong on the zeros, if there's going to be a 1 or not. So you get 8 over 120, and you subtract that to 5 over 20, you get 3 over 20, which gets you 1 over 40. And then let's do the most hardest example that I have found that turns out to be real cute number, as Mr. Bogart says. And that's number 5. Is you got x cubed from 0 to x cubed, and then you have square root pi. From square root pi to square root 2 pi, you have sine y all over x, uy dx. This was a semi-problem because I kind of forgot about integrals, but never mind about that. So you integrate it, you got all this, and remember, x is a constant in this situation because it's in respect to y, the integrand. So you do as always, you plug in the values corresponding to it. Now, what I told you before is to do the zeros, because this time that whole thing equals to x. So what you get is negative x cosine x squared plus x, and all that in the integrand from square root pi to square root 2 pi. Now we're gonna go a little bit fancy. Now we're gonna split the integral because we can, and we have from square root pi to square root 2 pi, and we have negative x cosine x squared, all respect to x, plus the other variable from square root pi to square root 2 pi x dx. So never mind the big line because I will show you later on what it means. So you integrate this part, and you find out that that actually equals 0 because all this sine of 2 pi or pi is 0. So you find that out. Then you do the other one. That's why there's an arrow. So you got this square root. So you have x squared all over 2 square root 2 pi and square root pi. Plug that in. You got 2 pi all over 2 minus square root pi squared all over 2. And then you get that. You square the numerators. You simplify it and you get pi over 2. Now, just to challenge my authority, we're gonna check if I'm right or wrong. And for number 1, it is 1 over 40. And for number 5, I told you it was going to be a cute number, and that was pi over 2.